But I thought I would put in a pitch for something the math club is doing shortly. There's going to be a trip to the Museum of Mathematics. Have you heard of that?
It's a very awesome place in New York where we're all going to have fun and eat pizza and just be awesome together.
That's me at the Museum of Mathematics.
What's that you're on?
It's a square wheel tricycle.
Were you able to actually ride it around?
See how the floor?
Oh yeah.
The floor has cycloids, arches on it, and the square wheels and the cycloids actually can go quite smooth ride. Sometimes a little hard to get started.
Understandable.
That's part of the display at the Museum of Math. So people should go to the Museum of Math. We're going to be driving vans down there. I possibly will be one of the drivers. I think there's at least one van, but certainly at least one. But there might be two if we have people interested in going.
Is it a windowless van? Are you all taking us into your windowless van?
Oh, it's windows.
Okay.
Why would you want a windowless van?
No reason.
Free candy written on the side. Oh, this is getting creepy right here.
So what else is good about the Math Museum? Or the Museum of Math?
Did I tell you that it's around the corner from the Museum of Sex?
I think you may have mentioned that before. Will we have time to visit both?
Did anyone just sign in a second?
No, you got distracted.
You didn't put in the password just to use it. Oh. He's actually good. No. You normally make a joke about that, but you know what's still not. Yeah, I might be a jerk, but not that much. So look, everyone looks skeptical all at once now.
Yes.
Can we go over one of the homework problems? I still don't understand.
Sure. Let me just get set up here and then
I know. And I always sit
Pick a different row?
No. But I like the wall. Yeah, I like the wall. I like having to turn this out.
Is it possible to turn down the air at all? Do we have any of those kinds of controls?
I think we're coming to the time in autumn when it gets nice and cool outside, so they turn the AC up and make sure that no one can turn it off.
That makes sense. If I recall correctly, they do something similar with the string where they try to keep all the way up in like May.
Yeah, you like this, the heat thing on focus. The other thing I really enjoy is in the summertime when the AC up so high that people open the windows to let the cold air out so that they can not shiver to death. Well, yes, we were just talking about the MoMath trip. Want to give people details?
Yes, give us the deets.
Okay.
It is not October 28th. We're going to leave over Southern to go to Manhattan. If you wanted to go by yourself for a student, it's $10. Parking. I parked somewhere and it was. It's a really nice place. It's very interactive.
How much will it cost if we're going as a group?
They won't go, they'll probably give us a discount.
Is it if it's 25 and over, we get a discount?
Oh, it's not that.
So, it's very interactive. History-wise, not very much, but it's really cool, like, interactive games and the gift shop is really cool. It's like Dr. Phil's office, but prices.
It's in February, so I don't think we're getting extra credit if we go. Did you say February? Wow, I can't hear. I really heard February 28th.
It's sooner than that, for sure.
I mean, we could go again on February 21.
I apparently can't hear.
So,
Did I show you that?
Yeah, you did. I'm telling you.
I was just showing everybody.
Look,
Okay,
she
Becky,
did say you
what
could go
homework
over
did you want to
October,
do?
but
okay, we all do it.
3.3, number 2. side now?
Yeah, do 1, 3, do 1, 2, 3, and 4.
Oh, okay. I'm thinking of the other side.
Yeah, so,
I'm not.
man, right.
Equals grid.
It sucks. When are we going to be able to catch up with her?
December.
Oh, it's only a couple months away. If anyone can do it, I'm sure you can.
Maybe. It's next child. Maybe like 18 years.
Alright. Well, no. Children mostly raise themselves around the time they're 8, right? So we need to worry about 7 more years.
Okay, number 2 says, find all right triangles with sides of integral length whose areas are equal to their perimeters. Right triangles. So that's nice because if you say x and y are the short sides, it's just x times y is the area. And the perimeter, that's what they've written there, x plus y plus e equals, why is it 1/2 of xy?
That's the area.
Because I screwed up, didn't I? Yeah, the area is, I mean, it's a triangle, not a rectangle, so it's half the rectangle. All right, so we've got x squared plus y squared equals z squared just because it's a right triangle. Give me a picture of it. So we have x and y as the shorter legs, and then z as the long leg. Its area is xy over 2, and its perimeter is just the sum of those 3 numbers. So if you say that you want the area to be equal to the perimeter, you get xy over 2 equals x plus y plus z. Wait, what? Then they say that implies this factored form of an x minus 4 times y minus 4 equals 8. How? I'm certainly not seeing that here. Right. But that's what they're claiming that it equals to. So this is in question. Let's put a question mark on that. But is that the same as x minus 4 times y minus 4 equals 8? Wait a second. There's something messed up there.
Yeah, do we need to
The
use...
symbol here I've used between them isn't the right thing. Because what I'm talking about is this equation equal to this equation. It's not, we don't usually use the equal sign there. So how about we just say like some kind of thing. One can be converted from the other to the other. Like that. So this is a great example of, you just do algebra with both sides until you find that they actually are the same. Or else you realize, wait a minute, they made a mistake in the book somewhere. What would you do with this thing? Boil it out? Yeah. So I get xy, first times first, minus 4x and minus 4y, and then plus 16 equals 8. Is there anything you'd like to do to this side to simplify a little bit? Some of them not liking the fraction. You know, I'm an anti-fraction sort of guy, so I'm going to multiply both sides by 2. And we have xy equals 2x plus 2y plus 2z. Well, wait a second. It's pretty clear that this jump in the minus 4x minus 4y and the 16 is on the wrong side of this equation if we want it to end up looking like that one. Okay? So let's subtract or add the right things to get this xy by itself. Oh, really? It'll be 4x plus 4y, and then minus say 16 gets us to negative 8. I'm not seeing how these things hook together, I'm really not.
You need to use x squared plus y squared equals c
Yeah, I
squared.
was gonna say
Oh.
factor it out.
Have we used that at all?
But yeah.
But I don't have x squared plus y squared equals. I mean, these are linear, right? I only have x's, and the only quadratic term in it is x times y.
Well, it doesn't say that x plus y plus z equals 1/2 xy implies, the second part it says that x squared plus y squared plus z squared, and that second part
Oh,
implies that.
it's the two of them together.
Yeah.
Weird. Do you notice how there's no z on this side?
Yeah.
But there is a z on that side? We can, but unfortunately, it's not z that we have, it's z squared. We have a rule for. Z squared could be replaced with x squared and y squared. Okay, let's do that then. So we have, let's replace it. The one equation says xy equals 2x plus 2y plus, it really says 2z, but we'll write that as 2 times the square root of x squared plus y squared. And versus the other equation says xy is equal to 4x plus 4y minus 8. Here's what I'm thinking, but if these things are really supposed to be the same, let's pull out the things that we definitely see. You see that 2x and a 2y? Let's pull out a 2x and a 2y. And the junk that's left over, maybe we can just work with that. So we'll write this as 2x plus 2y plus another 2x and another 2y and a minus 8. Oh, that looks like 2 times something, right? So that's getting closer. Let me just, yeah. No, I don't want to do this with the eraser. So one more line here. It's 2x plus 2y plus 2 times x plus y minus 8. Minus 4, sorry. So is it possible that x plus y minus 4 and the square root of x squared plus y squared are the same?
Sometimes.
When? Well, maybe if you got a right triangle. You're right. I mean, that's a conditional equation, right? So we're hoping it's true because we need the condition. We're actually on a right triangle. I think we're almost there. When is square root of x squared plus y squared equal to x plus y minus 4? Wait a second, I can do this, I think. Because square root of x squared plus y squared, that's z. Another way to formulate this is to say z is equal to x plus y minus 4. Well, maybe I'm wrong. I know what the sum of x, y, and z is. No, I don't really know it for sure. But, I'm not able to get to what their hit says. I'm sorry. Yeah. I'm sorry.
I think I have it. I have x plus y plus z equals to 1/2 xy. And then I substituted in for the z the square root of x squared plus y squared. And then I did out the math into a long set of equations until it it canceled down and then it gave me the implied thing, like the implied thing is.
Oh, so you just kept
answer.
working with that side?
Yeah, I just went down from
Mind if I
here.
just play your work?
I think it's pretty clear. It's clear to me, and, you know, not everybody reads this.
Let's go back now.
Stay deadly better.
Let's see what you got here. So you started with x plus y plus z is half of xy. Replace z with square root of x squared plus y squared like that. And what's your next line? You move things to the other side?
Yeah, I swapped.
What inspired you to do that? To move the radical to one side?
I just didn't want to radical on the other stuff. It's easier to simplify.
Okay, that's good. I probably would have
I
left
could
it on where it is
I
and
could
moved the other
always flop,
side.
I think I ended up having to flop it back later, so it was really pointless, but at the time, I didn't like the radical with everything else.
Okay. And then you squared both sides.
Yeah.
I like that, so you just mark the square here, and here we can just take away the radical. You also took away the minus sign.
Yeah,
Is that okay?
I did it not do both sides? No, because I squared it.
Because you squared it, right? So the
Yeah.
minus sign would go away.
I think I did the right math, but you questioned me, so now I'm trying to.
No, I'm not questioning you in that sense. I'm just like, anytime you see a string of algebra like this, you sort of go through and make sure you agree with each side. It's not like bad questioning, I trust you actually.
So then I did out the,
So
I foiled it out.
you have to multiply that out. Now, it's more than foiling,
Well,
when it's that.
It's, I still call it foiling even though it's like multitudinal foiling.
Multi-foiling. I have to show something right now because I love this way to multiply.
Okay.
And maybe you've seen it before, but if you have a three-term thing, a trinomial, and you're multiplying it by itself, there's a total of 9 terms that come from distributing. And the nice way to get them all and make sure you don't miss any of them is to create a little table so that you make sure everything from one polynomial gets multiplied by everything from the other polynomial. This is the table method for multiplying. Okay, so we have x plus y plus half xy or xy over 2.
Minus that.
Minus that? And then we'll have x and y and negative xy over 2. And now, so I made a column headers for the terms of the polynomial and row headers for the terms of the polynomial. And we'll multiply it all out by multiplying column and row headers to fill out an entry. So like we'll get an xy here. We'll get minus x squared y over 2 there, that's ugly. Here's another xy. There's y squared in the middle, y and y. You following what I'm doing here? This one right there will have minus x squared y over 2 again. Here's a minus xy squared over 2. What goes in this end of this row here? Minus, wait a minute, it's this one, right?
Yeah.
X, y squared over 2. Then we'll stay up here,
Negative x squared, y
X squared, y
squared.
squared.
negative and negative, so they cancel. So it's x squared, y squared over 4. And then, you know, you still have to combine the common factor. What are they called? Like terms, right? The like terms get into combined. So final answer is x squared. Let's pull out the easy stuff first. There's x squared plus 2xy's plus y squared. That's looking nice. That's like x plus y squared, right? So I might want to leave that alone. And then this other stuff with the over 2's, but there's always 2 of them, right? Which are out of terms. So this is negative x squared y. And these two are going to give us negative xy squared. And the last one is all by itself, x squared y squared over 4. Now let's just check Asana, did you get that?
Yeah.
It was all.
Yeah, it's
So we got x squared, like I got a point where you can see it. X squared and y squared and 2xy. That's minus the one that's got x squared, that's minus the one that's got y squared. There's the quarter. And, yeah, okay, good. So I had to check her out. You're out going on that complicated. No.
I tend to make mistakes.
Yeah, plus I thought it was a good opportunity to show
Yeah,
people
I
this,
like
this
that.
technique.
I usually just hold my finger on the first turn and go, okay, times it by itself, times it by this, and move down and
Yeah.
write it.
So
Then I
you've
hold
got
it
a
on-
systematic way to go through it
Yeah.
too. Okay. Actually, this technique we just did gives you a way to do products in your head. One of the things I really like about it is you can square numbers in your head if you really get good with this. Like if I wanted to write 231 times 231. Wait, I should say 200, 231. But you know, it's just filling out the table. And I don't know, that'll be with four zeros. That'll be 6 with 3 zeros. That'll be 200.
I see where you're
Fill
going.
it out. You can do it with numbers too. It doesn't have to be polynomials.
So then I moved the x squared and y squared over,
Okay.
simplified it down.
I'm looking at this. Sorry, this line right here, where you've got x squared plus y squared on both sides. Did you just take them away? Well, that's what you did. Yeah.
I moved it over, and then from there I simplified, and if you go all the way down, you get what they said it implies.
Okay,
So like I proved the implications,
that's good.
and then from there.
So wait,
I-
you factored out x, y out of everything.
The XY canceled because,
No, it's factored out, right?
yeah,
And then you said, look, if I'm going to get 0, it could be because that's 0, or it could be because this is 0. Was x times y likely to be 0? What would that mean? That would mean that either x or y was 0.
yeah, I had this figured out.
Okay, could x or y both be 0, or one of them be 0? What are x and y?
This is sides of the triangle.
The lengths of a triangle, they're not going to be 0. Right? We would not do that. That would be the degenerate case. So it's fair to cross off that x, y. Well, but this is the thing that's important. If it's going to be a proof, we not only have to be able to justify each step, not just do it. Okay, so cool. Then you end up with multiplying by 4. Where did that come from? Because you knew you wanted to get to this other
Well, I
thing.
also want to get rid of the full credit.
Okay. And that makes good sense, right? I'm loving it. And you didn't multiply the 0 by 4. So it's still 0.
That's some bad math right there.
Yeah, so of course that's going to be, that's valid. And where are we supposed to be? Well, except for adding 8 to both sides. That's also very good. Okay, but, you know, even if you couldn't verify the algebra, could you use their hint? It said the condition given is equivalent to that quadratic. X minus 4 times y minus 4 equals 8. So can you find solutions to that?
Using that quadratic, you find the solution, so the 5, 12, 13 triangle and 6, 18 triangle.
So how does the algebra of that work out? You've got x squared minus 4x minus 4y.
Plus 16.
I'm sorry, I said x squared, it's xy. Plus 4x minus 4y equals 8. No, plus 16 equals 8. Usually you want to take a quadratic formula and mess with it until you get 0 on the right-hand side. So we want to subtract 8. And can this be factored? Oh, you know what we could do? Oh, wow, that's sort of cheating. I was gonna say, we could do something the Greeks would never have done, is plot a graphing calculator, so see where the curves are. Is that okay? Sure. I don't think, somehow I don't feel like that's okay. How about this? I'm gonna show you another approach that, again, the Greeks would have thought of, but maybe you would have. There's nothing so special about X and Y at this point. I mean, we've just got an algebraic thing. Why not create new variables that are related to X and Y? So let A be X minus 4. And B be Y minus 4. Can you re-express what they've written there as in terms of A and B? The product of X minus 4 and Y minus 4 equals 8 is the same thing as A times B equals 8. So you can get answers by going, well, I'm just looking for a pair of things that add up to 8. I mean, add up. I just said add up, didn't I? Multiply up. Their product is 8. But there's other answers in there. This is a hyperbola. It's like y equals 1 over x. So it's got lots and lots of solutions on it, but I think we were after whole number solutions. And I'm pretty sure it's A is 2, B is 4. It's going to get you 1. And then vice versa to get you the other. Is that the most used? Oh no. Oh wait, that would give B is 4 would give me Y is 8. Oh no, that's okay. I gotta invert these relationships so that X is A plus 4, Y is B plus 4. So this gives us 6 and 8, and then that's 6, 8, 10. And if we did
Hold on, that didn't work. What?
A equals 4, B equals 2, then you're going to get 8 and 6, same one. What were the values for these A and B that give you the 5, 12, 13?
1, 2, 4, and 8.
Oh, yeah.
So you want.
Right, this is 1 times 8. A equals 1, B equals 8. And that gets you 5 and 12 and 13. It's kind of fun. The different ways to factor 8 turn out to be the ways to get at the answer. 8. I like that trick of changing the variable to something that's nicer for you. I think I hesitate to do that. So actually, it's getting to the time when we should start the quiz, but I have a slight problem. I forgot to come in and Xerox it this morning, so I have a quiz on my computer. I don't think that's what we want to do.
So should we just take it as a group?
Can you take it?
You do it, take them.
Home.
I was going to suggest we just wait till Monday and I'll get Xerox.
I go around that.
But I think several people came to my office and were concerned about the difficulty level of this homework and were worried that the quiz was going to be similarly difficult. I don't think you'll find this quiz that hard. I'm not saying I'm postponing it because I think it's hard. I'm postponing it because we're running short of time, and I really did want to talk a little bit more about, what's his name? Eratosthenes.
If hard quizzes like this, we're going to throw it.
Yeah, we would. So, did it make sense? No? So, that first reminder is wrong. This will be Monday. We talked so far up about Eratosthenes' accomplishments. We mentioned he had this machine that would solve the Boolean problem, and that he was able to figure out how big around the Earth is, the distances through the sun. But I started to talk about his sieve method for finding the primes, and I think this is perfect. We've got just enough time for us to actually do the sieve. That is, you will sieve the way Eratosthenes used to.
this go up to?
I also have Osama, Michael, Kevin, Yaris. So what is this Civic Veritas thing? You recognize that you could figure out which numbers are prime by focusing on which numbers aren't. The idea was to get rid of the composite numbers. And if you do it in a step-by-step way, you'll be able to guarantee that you've eliminated all the composite numbers up to a certain point. Okay? So let me just point out this fact about the way numbers work that you should know. If you've got a number somewhere down the line that looks like a product, that is a composite number, so you've got something composite. What composite means is it can be factored into two or more things. Right? So n will equal to a times b. Yeah. Well, one of those two numbers is smaller than the square root of n. Why is that true? Can you think about why that would be the case?
Well, if they were both bigger than the square root of n, then when you multiply this something bigger than the square root of n times something bigger than the square root of n, you're going to get something bigger than n.
Yeah, that's it. So what did you start with? You started off with the negation of it. In other words, you did a little miniature proof by contradiction.
I'm just not awesome.
I'm proud of you. So if this wasn't true, then we would have both of them larger than root n. Now multiply and you get something bigger than n. Follow this logic? Okay, so one of them is smaller than root n. This is the fire under the hood for those Civic Veritasians. If you go looking for proof that some number is composite, you don't have to search through all the primes. You just search up to the root of n. If you haven't found a factor by the time you're at root of n, you're not gonna. Right?
Should be less than or equal to, because like if you had 4, this would be close to 2 times
Less than, right?
Well, they
But
could
then
both
you-
be the square root.
2. Yeah,
Oh, they could be less than or equal to?
yeah.
Alright.
Just clarify
No,
for myself,
no.
don't get mad.
I'm not mad, I'm just like embarrassed. I think I just was shortening it up because I didn't want to write or equal to. But, you're right. So let's give an example. Is 91 a prime number? You know that, but how do you verify this? How far do you have to search looking for factors of 91? Well, you know 7 is a factor too, so you're using pre-knowledge. She had the right answer. 91 is close to 100. Take its square root, it'll be close to 10. So if you look for primes smaller than, you look at primes smaller than 10 and ask, do they go into 91? 2, no. 3, no. 5, no. 7, oh, I have to divide, but yeah. Right, so we find that 91 is a composite number by looking at things really far from it, really much smaller than it, square root precisely. Okay. So let's do this. Why don't we do this in small groups? Groups of 2 or 3. Here. I gave you 2 for. They're not working. No. There's a story of the general who was the guy who ran the National Security Agency when it first formed. And so the first thing they did was scour the world for mathematicians, and they hired all these mathematicians to come there. So he was talking to a visitor, a distinguished politician, and told him, around here, an extrovert is a man that looks at your shoes while he's talking to you. So you're like falling into the mathematician mode.
Yeah.
Seriously, come on, Brian. So what are you supposed to do?
Sorry.
You're already done, right? Okay, wait a second.
No, we're working on it. I skipped 3.
You can't skip.
I accidentally skipped 3. So,
Okay.
I'm fixing that.
So first you circle 2, because that's the smallest number that's... Okay, why don't we circle 1?
It's not exactly prime.
It's actually the definition of primes. A number's prime if it's bigger than 1 and can only be written as a product of 1 in itself. So it's just, they took care of 1 in the way they describe what a prime is. It's not 1. 1 doesn't count. So you can just forget about 1, but 2 is the smallest prime. And now the sieve idea here is to kill off anything that's not prime, and 2 is to blame for it. Right? So that is, 2 has been circled, but every other even number gets killed. So you can actually find them in columns. You can do what you're doing. Every even number is going to be like, I would just go.
That's a good idea.
Oh, yeah, that whole column is right. You're working so hard, just sort of with a line.
I like squiggly lines better.
Okay, now what is the smallest number that has not been crossed out? 3. You just found the next prime. Okay? But now you got to get rid of all the multiples of 3. Don't jump the gun and start doing 5. Right? The next stage is knock out the multiples of 3.
Yeah, that's...
You are working so hard doing that. See, look our
It's diagonal.
Wait, Brian, probably will tell them.
You can just draw lines. And it's a challenge to see how do you draw the
Yeah.
how do you use lines to knock out all the things that are multiples of 3. Start by crossing through them off and you'll see the pattern.
So 19 is fine. Okay, right.
Are you seeing these guys line on lines with the lines are diagonal?
Yeah, no. So that's fine.
No, that's the 3, 12, and 21.
All the 11s are pretty crossed out.
6,
So 9 is
You guys are almost working with pretty here, but I'm not going a lot. So 3 quarters, big triangle. Huh? You just don't want to move chairs? Is that it? So, what a lot of people are doing is just knocking out all the even numbers in a column. By just drawing a line right through it. Close off.
That's easier, 17.
So it starts with 4 and it's all the So, once we're at 1, no, I said, leave 1 out because 1 is not a prime. The first prime is 2. The real problem with circling 1 is then you would supposed to be crossing off every multiple of 1. And you've already finished. Cross off every time. So, but 2 is the first prime.
That's,
And then
No,
you
I
knock
just
off
like
that
try
back
those.
column.
it's 90, 27, 37.
Because those are
It's
all
like
kind of
that's
the
21. No, it doesn't go that. 3, 9, 5, 8, 8. I don't know where it's these girls.
Are you really up to multiples of 29? Or
On
did you
that,
get,
wait, this way.
greedy and playing
Yeah,
primes?
go
and
nine.
really-
I was going this way.
Yeah,
I
it's
got
the
the
other
board.
No, I'm on 29.
Yeah.
Okay.
So why? Why do you want 29?
Good.
It is, but it's like 1100.
Yeah, good idea.
No, that's
That's what I
right.
was saying up there, I was telling you when to stop.
I'm like, no.
Okay, I want to keep
Oh,
going.
that's right. It's divisible
Well, you could, but you need a
by
percentage.
Yeah.
Just because
So I can just circle everything
Well,
without
where
slap.
Like, literally.
Yeah, as soon as, you'll notice that when you did 29, everything you tried to cross off had already been
Well, I'm
crossed
saying
off.
make this cool to handle.
Okay,
That is
so
kind of
5 is
cool.
That's why I love it. Okay, I got it. It's the only one I'm trying to remember. The other already all done.
It's
I'm
everything.
doing this very mechanically, okay? Not any fault whatsoever.
Yeah, everything else can help us out.
Minus the
Everything on the page is fine, up to,
first
so it's really
and
square of 11, 121.
Yeah, it's up to 8.
I had a good way of counting. Did you see my 30 minus 1? That worked well for me.
Did you get the pattern on multiples of 7? That was one of the more hard ones to find. It's a, like the chess, so
Oh, yeah.
7 to 28.
Yeah, 1, 11.
And then, where's the other one? 14 here, and down on the other.
Most of 7 was already crossed out.
Yeah, right. In fact, what is it, 91 is the only oddball, I think, or maybe 49, so. How's it going, guys?
I know, right? Kind of
You're
weird.
not 7.
Oh, she's doing 7 already. Okay,
Never mind.
so you're doing 3. What do you, where do you think you're going? Nine?
Yeah.
6, 15, 14, 18, we're all getting close off. You can do these like lines on a 45-degree angle. You don't know pretty much. It's interesting, there's a lot of different patterns.
I was like, let's just keep going. Oh,
No,
wait, these are all
this is-
crossed
that's
up. Oh, wait,
not-
these are all crossed up.
I know, right?
These are all crossed up.
Exactly.
There's one from 9, and that way.
That's just like he asked,
And it
he was
actually
asking
goes
why
around
I
the
crossed
edge,
up
it
X,
looks
I'm
back.
like, I had a reason.
Very-
What was the reason? I had a reason.
Your variable says by X1.
Get something
It's like
close.
X, Y cancels
Yeah.
because it's irrelevant,
Um,
I don't
You're
care
50, you're
why.
doing 11 actually.
I knew it while I was doing it, otherwise I would have
It's
done
already
it.
all crossed off. That's a very good observation. Sometimes we just get.
The reason why we point out specifically that X and Y can't be zeros because we divide both sides of X, Y, that if neither X or Y is 0, then it becomes wrong.
No, I understand, I just hadn't,
No,
I didn't write it
is a
down, so I
prime.
wasn't doing a proof, I was just doing my,
The point is, these numbers are all smaller than 100, so their
Right.
smallest factor is smaller than 2.
I perfectly oversimplified the one before.
So we discovered the compositeness of those numbers when we used
This is
2,
what
3, 5,
satisfies
7.
that.
You're already.
different methods.
Exactly.
Nice.
All these circle ones
Well, the circled ones are the primes you set with,
level.
and everything that hasn't been crossed off is a prime number.
Now,
Yeah, that's the thing. I'm
So
like,
it
now
looks
I
like you
love
forgot
that
to-
because when I'm actually
Or multiple
teaching
for 5.
algebra, I need a different point of view, so if my kids aren't getting the way I'm doing it, I can
No,
express
you
it
don't
in a
but
different
when you
way.
Exactly.
So I love that, that's
Yeah.
great.
You're going to teach ones that end in a 5 and the ones that end in a 0.
7 through 12, but I would like to
Oh, your
be
slashes are
somewhere
little,
in the
okay.
9th grade area to count.
Yeah, I'm actually going for my lessons as well. So, as long as we go to
I'm
7.
only getting my
Then you finish.
undergraduate.
So, and if you notice what,
Oh, yeah,
just what you
so
just
you can,
said,
get your
try
master's
to
warrant.
cross off multiples of 11, they're already done.
Yeah, physics. Yeah.
Which is kind of what this is about.
Two groups, right?
I'll teach whatever they give me to teach, but I would really enjoy teaching algebra, whether it's pre-algebra all the
So
way
it
up
sounds
to
like people have
algebra
honestly
2,
finished.
you know.
Yeah, like up there.
That's my happy area.
Okay,
I know what you mean.
It's not just that I'm good at it, I was also in high school, I tutored it a lot, and was good at explaining it in different ways, that's the whole.
let me run through this real quick. Somebody's paper here, so you made a mistake on that, but the first prime is 2, we don't deal with 1, because think about what happened if you sift with 1. You circle 1 and then you remove all of its multiples, and you've removed every single number.
So nothing is prime, only one.
Yeah, no, that's not quite what we wanted. So why the definition of prime says it's a number bigger than one that has no factors other than itself. But here's what I was trying to suggest to people to do is cross out all the even numbers under. You see how in columns, the even numbers, numbers even if it ends in an even digit? So you've got, we'll get these all at once. And then the first number that's not crossed off is 3. And this was a little harder pattern to find, but the multiples of 3 land on diagonals like that one, which comes back in on this side. And you knock off a whole bunch of the multiples of 3 that way. But also 6 and 15 and those guys. Comes off the edge and goes back in over here. And 9, good. And then that's those two. So far we've just taken off the multiples of 2 and 3. 5 is really easy. Where are the multiples of 5? Right under it. But also this column down on the end. But that's okay. We'd already crossed them up because they were all even. And the last one we're going to need to do is 7. Why? Because the square root of the table only, the part of the set of integers I've given you only goes up to 100. So the square root of 100 is 10. We only need to sieve using primes smaller than 10. And finding where the 7 multiples are, that's the challenge. So 14, 28, where else? 21, that's already done.
Would that be short like that?
Yeah, there is a pattern. You go down 2 and over 1. Get a thing.
Wait, what is that pattern for?
It's the way a knight moves.
For
in
7?
chess. For 7.
Oh.
Down 2 over 1, and
Oh
7.
my
You
gosh.
can also go down 1 and to the left 3.
Wait, down 2 from where though?
Well, I started at 7 and went down 2 over 1.
Yeah.
And then I've got to find, what else is a multiple of 7? 14, so down 2
From
over 1.
there,
What's that? Let's see, forward across. There's 77, that's a new cross there. I think there's more that I haven't gotten to yet.
There's 35.
No, I got 35.
You can start from.
How about,
It's just I'm seeing these two kind of rows of diagonal stuff. I'm expecting one in here somewhere. Hey, isn't 63 a multiple of 7?
It is.
Yeah,
Yeah.
so that one should have gotten double crossed out. 42, oh yeah, 42. There it is. So now I think I've crossed off everything. That's either even, multiple of 3, multiple of 5, or multiple of 7. What remains is all primes. And I think people tend to go, okay, now I'm going to circle everybody else. But I wouldn't do that, just like maybe underline them or something. 11, 13, 17, 14. Recognize those? They're underneath. What Veritas, well, this goes further than what we've done. That's a mechanical way to produce a list of the primes, and you can know for sure that it's good up to a certain point. It also has ramifications in counting how many primes there are, and that's a modern problem. It's called the prime number theorem, which finally settled in the 1800s. How many primes are there? Less than 1 million. You don't want to actually generate all of them and try to see, but the sieve gives you a way to kind of count by instead counting the composite numbers. For each number, it's been crossed off some number of times when you sieve, and you can sort of, well, you have to remember that you're counting multiple crossing out, so you have to kind of take that into consideration. But it's still possible to come up with a formula for how many primes and plug in your number to get it up. Asymptotically, it's very interesting. It's close to the natural logarithm. The natural logarithm of the number tells you how many primes are less than.
That's a suggestion.
So when we do the quiz on, okay. Yeah, so, okay, we're done. Yeah, thank you.